The universe is not just expanding, it is speeding up. This fact, discovered just a few decades ago, shattered our cosmic expectations. Something is pushing space itself apart faster and faster, and we have no idea what it is. We call that something dark energy, and it is the single greatest mystery in all of science. It makes up about 70% of everything that exists, yet we cannot see it, touch it, or explain it. By the end of this journey, you will have explored 30 of the most brilliant, bizarre, and mind-bending theories that physicists have devised to crack this cosmic code. We will venture from Einstein's biggest blunder to ghostly particles in extra dimensions, from the terrifying possibility of a cosmic rip to the idea that our entire reality might be a hologram. Each theory is a different path through the same profound darkness, a testament to human curiosity staring into the unknown. So, are you ready to question the very fabric of reality? Our journey begins not with a discovery, but with a mistake. Albert Einstein, the architect of modern gravity, faced a problem. His beautiful equations of general relativity described a universe that was either expanding or contracting, a dynamic cosmos in motion. But in the early 20th century, every astronomer believed the universe was eternal and unchanging, a static stage for the stars. To make his theory fit this belief, Einstein introduced a fudge factor, a mathematical term he called the cosmological constant. It represented a repulsive force, a kind of anti-gravity woven into the fabric of space itself, perfectly balanced against the pull of matter to keep the universe still. Later, when Edwin Hubble proved the universe was indeed expanding, Einstein called this addition his greatest blunder and discarded it from his equations. Decades later, that blunder made a triumphant and shocking return. When astronomers in the late 1990s discovered the expansion was accelerating, they needed a source for that push. The simplest solution was already written in the textbooks. They dusted off Einstein's cosmological constant and gave it a new meaning. No longer a tool for a static universe, it was reinterpreted as a fundamental property of the vacuum of space itself. According to quantum physics, empty space is not truly empty. It is a seething, bubbling quantum foam where virtual particles flicker in and out of existence in an endless dance. This activity should give the vacuum a baseline energy, a constant pressure that acts like a spring embedded in the cosmos, pushing everything apart. This is theory number one. Dark energy is simply the cosmological constant, the intrinsic energy of empty space. Its greatest strength is its elegant simplicity. It fits the observational data remarkably well with just one number, that constant energy density. It requires no new particles or forces beyond our current understanding of physics. It is the default, the simplest answer on the table. But this simplicity hides a problem of cosmic proportions, a flaw so severe it is often called the worst theoretical prediction in the history of science. When physicists calculate how much energy this quantum vacuum should have based on known particles and forces, the number they get is unimaginably huge. We are talking about a number with 120 zeros after it. The energy density predicted by theory is one followed by 120 times larger than the tiny, gentle value we actually observe from the acceleration of the cosmos. This is the vacuum catastrophe. It is not just being off by a little. It is like predicting a tidal wave that could drown a continent and instead observing a single, gentle ripple in a pond. The cosmological constant works as a description, but as an explanation, it leaves us with a gap in understanding wider than the universe itself. Such a colossal mismatch means the search cannot stop there. If the simplest answer creates the biggest problem, perhaps dark energy is not a constant at all. Perhaps it is something alive, something that evolves. This brings us to theory number two, a concept with a name pulled from ancient philosophy, quintessence. In ancient Greek thought, the cosmos was made of four earthly elements: earth, air, fire, and water. But the heavens, the realm of the stars, were made of a perfect fifth element, the quintessence. Modern physicists borrowed this poetic name for a radical idea: that dark energy is not a static feature of space, but a dynamic, cosmic field that fills the universe like an invisible fluid. Unlike the rigid, unchanging cosmological constant, quintessence is what scientists call a scalar field. Think of it like the temperature in a room. The temperature has a single value at every point, and that value can change from place to place and from moment to moment. Quintessence is like that, a field whose energy density can vary across space and, crucially, evolve over the vast stretches of cosmic time. This fluid has a bizarre property: negative pressure. Imagine trying to pull the plunger on a syringe filled with ordinary air. It resists, it has positive pressure. Now imagine a syringe filled with quintessence. When you try to pull the plunger, instead of resisting, the fluid helps you. It actively pulls outward, creating more negative pressure inside. On a cosmic scale, this negative pressure acts as a repulsive force, accelerating the expansion of the universe just as we observe. The true appeal of quintessence lies in its dynamism. The cosmological constant presents a cosmic coincidence. Why did dark energy's repulsive push become strong enough to overcome gravity's pull at roughly the same time that complex life emerged on Earth? With a constant, it is just a lucky accident in cosmic history, but a dynamic field can offer an explanation. Perhaps in the early, dense universe, the quintessence field was weak, dormant, overshadowed by the fierce pull of gravity and radiation. As the universe expanded and thinned out, the field could have slowly awakened, its influence growing until, a few billion years ago, it finally became the dominant force, initiating the era of accelerated expansion we see today. This solves the coincidence problem elegantly. It was not luck, it was a natural evolution, a changing actor on the cosmic stage. Yet for all its elegance, quintessence brings its own profound questions. What is this field made of? What kind of particle, if any, carries its force? How exactly does it change over time? We have no direct evidence for its existence, only the tantalizing possibility that it could explain the timeline of our universe's acceleration. It is a ghost in the equations, a theory of beautiful potential, waiting for a signal from the depths of space to confirm its reality. Perhaps the entire quest is looking in the wrong direction. What if dark energy is not a substance or a field at all, but an illusion? A cosmic mirage created because our fundamental theory of gravity, Einstein's masterpiece of general relativity, is incomplete. This is the radical premise of theory number 3, modified gravity. The idea is audacious. For over a century, general relativity has passed every test with flying colors, from the bending of starlight around the sun to the precise orbits of binary pulsars. It is the bedrock of modern cosmology, but what if it only works perfectly within the confines of our galactic neighborhood? What if, on the vast, empty scales of the entire universe, the rules subtly change? Proponents of this view argue that inventing a mysterious, invisible energy making up 70% of reality is a drastic step. Maybe it is simpler to adjust the equations of gravity themselves. One of the most studied versions of this idea is called F of R gravity. That R stands for the Ricci scalar, a mathematical term that essentially measures the curvature of spacetime. In Einstein's original equations, this term has a simple, linear relationship. Think of it like a spring that obeys a straightforward rule: pull it a certain amount and it pushes back with a proportional force. In F of R gravity, that relationship becomes a function denoted by the letter F. This means the behavior of gravity can change depending on the environment. In regions of high curvature, like near stars or within galaxies where matter is dense, the theory is engineered to behave almost exactly like Einstein's relativity, ensuring it passes all the stringent tests our solar system provides. But in the vast, low-density voids between galaxies, where spacetime is only gently curved, the modified function takes over. Here, gravity itself could gain an extra repulsive kick, mimicking the effects of dark energy and driving the accelerated expansion, all without adding a single drop of exotic energy. The universe accelerates because gravity, on the grandest stages, simply plays by different rules. This is an elegant mathematical sleight of hand, replacing a mysterious substance with a refined law. Yet elegance faces harsh practical tests. The primary challenge is making a theory flexible enough to explain cosmic acceleration while remaining rigid enough to survive close-up scrutiny. The solar system is a high-precision laboratory for gravity. We know the exact orbits of planets, the trajectory of light passing the sun, and the data from spacecraft like the Cassini probe. Any modification to gravity must leave these exquisitely measured phenomena untouched. Crafting an f of r function that is active across billions of light years but completely dormant here in our own cosmic backyard is a formidable tightrope walk. It forces theorists to build in what they call screening mechanisms, mathematical cloaking devices that hide the modified gravity in dense regions like our solar system. While such models exist, they can feel engineered, like a complex fix for a single problem. Furthermore, if modified gravity is real, it should leave distinctive fingerprints on how galaxies cluster and how the large-scale structure of the universe forms, predictions that upcoming telescopes will hunt for. So the question remains, is the accelerating universe a sign of something new filling the cosmos? Or is it the first crack we have seen in our deepest understanding of how space, time, and gravity truly work? But what if the two great shadows of cosmology are actually one? We have spent decades searching for separate explanations for dark matter, the invisible glue holding galaxies together, and dark energy, the mysterious force tearing the cosmos apart. Theory 4 proposes a breathtaking simplification that they are not two entities, but two faces of a single, exotic substance known as the Chaplygin gas. Named after a Russian physicist who studied airplane wing lift over a century ago, this model suggests the universe is permeated by a perfect, unified fluid with a truly bizarre property. In ordinary gases, like the air in a balloon, pressure and density are linked. When you squeeze the gas, its pressure increases. The Chaplygin gas defies this intuition. Its pressure is not positive but negative, and that negative pressure is inversely proportional to its density. This strange mathematical relationship gives it a chameleon-like ability to change its cosmic role over time. In the dense, crowded early universe, the Chaplygin gas had a high density. According to its unusual equation, a high density means its negative pressure is very small, almost negligible. In this state, it behaves exactly like cold, pressureless dark matter. It clumps together under gravity, providing the scaffolding for galaxies to form, acting as the cosmic glue we have attributed to dark matter. But as the universe expands, this fluid thins out. Its density drops, and here is the twist: as its density decreases, its negative pressure grows stronger and stronger. In the modern, sparse cosmos, the fluid's density is low, so its repulsive negative pressure becomes dominant. Now it stops acting like clumping matter and starts pushing space apart, perfectly mimicking the effects of dark energy. One fluid, two eras, a seamless transition from the architect of structure to the engine of acceleration. It is an idea of stunning elegance, solving two of the universe's biggest puzzles with a single, unified entity. The appeal is undeniable. Why invent two separate unknowns when one could do the job? Yet the universe rarely grants us such neat solutions. Observations have placed this elegant idea under immense strain. The primary challenge comes from the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light carries a precise imprint of how matter was distributed in the infant universe. The patterns we see strongly suggest that the dark matter component behaved in a purely pressureless, particle-like way from the very beginning. The Chaplain gas, in its attempt to be a unified fluid, inevitably retained some tiny, residual pressure even in its early, high-density phase. This subtle pressure prevents it from clumping quite as efficiently as the flawless, cold, dark matter required by the data. It leaves a faint but detectable signature that, so far, does not match what we observe in the detailed maps of the early cosmos. Furthermore, studies of how galaxies cluster together in the more recent universe also seem to favor the two-component model. The elegant bridge between the two dark phenomena begins to look more like a tightrope that is incredibly difficult to walk. The Chaplain gas remains a beautiful and influential thought in theoretical cosmology, a proof of concept that unification is possible. It challenges researchers to ask if a more sophisticated version of this idea could one day fit all the evidence, or if it stands as a monument to a simpler, more unified cosmos that might have been. Elegance gives way to existential dread in our next theory. The previous ideas, from the cosmological constant to quintessence, operate within a specific mathematical boundary. They are described by a number physicists called the equation of state parameter, denoted by a lowercase w. For the simple cosmological constant, this value is exactly -1. For quintessence, it can vary but is always greater than -1. But what if the true nature of dark energy is not just strange but monstrous? What if its W is less than -1? This is theory number 5, phantom energy. The name is perfectly chosen, for this is a ghost that does not just haunt the cosmos, it seeks to annihilate it. To understand why, picture the universe's expansion as a tug of war. On one side, you have the gravitational attraction of all matter and dark matter, pulling everything together, trying to slow the expansion. On the other side, you have the repulsive push of dark energy. For the cosmological constant, that push is steady and unchanging. Its energy density remains constant as the universe expands. But for phantom energy, something far more sinister happens. Because its equation of state is less than -1, its energy density does not stay constant or decrease as the universe grows, it actually increases. Imagine a spring that, the more you stretch it, the harder it pushes back, but with a supernatural twist. This cosmic spring pushes back with a force that grows stronger faster than the stretching itself. As the universe expands a little, phantom energy becomes denser, which makes it push harder, which makes the universe expand faster, which makes the phantom energy denser still. This creates a runaway feedback loop of acceleration, a vicious cycle with no natural limit. The consequences of this escalate from dramatic to apocalyptic on a clear timeline. Billions of years from now, the accelerating expansion would first sever the cosmic web. The delicate filaments of galaxies connected by gravity would be stretched and snapped apart. Our local group of galaxies, including Andromeda, which is on a collision course with us, would become an isolated island in a rapidly emptying void. But the horror does not stop at galactic separation. As the phantom energy density continues to soar, its repulsive force would eventually overcome the gravity holding individual galaxies together. Stars would be flung from their galactic homes, sent careering into the deepening darkness. Then it would come for the stars themselves. The force would grow so powerful it would exceed the gravity binding each solar system. Planets would be ripped from their orbits around their parent stars. In the final moments, mere minutes before the end, the phantom force would surpass the very forces that hold matter together. The gravitational pull holding a planet like Earth intact would be overcome. Our world would be violently torn apart. Then, atoms themselves would be shredded, nuclei split from their electrons. Finally, in the last inconceivable fraction of a second, spacetime itself would be stretched apart at a rate that becomes infinite. The fabric of reality would rupture in a cataclysm cosmologists call the Big Rip. It is not an explosion from a point, but a terminal stretching of every single point away from every other point until all structure, all physics ceases to exist. The chilling question is, could this be our future? Current observational data from telescopes measuring the expansion history of the universe do not yet rule out phantom energy completely. The measured value of W is very close to -1, but the error bars, the range of uncertainty, still dips slightly below that fateful threshold. It is a slim possibility lurking in the shadows of our measurements. Future missions like the European Space Agency's Euclid telescope and the Vera C. Rubin Observatory aim to measure W with exquisite precision, to finally corner this phantom and determine if our universe is merely expanding, or if it is, in fact, doomed to unravel. From the terrifying specter of phantom energy, we turn to a theory that questions the very nature of reality itself. The holographic principle is not just another idea about dark energy. It is a radical reimagining of space, information, and where physics truly happens. To grasp it, we must first confront a strange paradox. In the 1970s, physicist Jacob Bekenstein made a startling discovery about black holes. He found that the maximum amount of information or entropy a black hole can contain is not proportional to its volume, like you would expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon, the two-dimensional boundary that shrouds it. This was the first hint that the information describing a volume of space might not live within that volume, but could be entirely encoded on its surrounding surface like a cosmic barcode. This idea evolved into the holographic principle, a cornerstone of modern quantum gravity research. It proposes that our perception of a three-dimensional universe with depth and volume is an illusion. All the information needed to describe everything within a region, every star, every atom, every vibration of energy, can be perfectly represented on a two-dimensional surface that encloses it. Think of it like a hologram on your credit card. The flat, shiny sticker contains all the data to project a three-dimensional image when light hits it just right. According to this principle, the universe itself might be a vast cosmic hologram. The three-dimensional world we experience is a projection from a two-dimensional surface at the farthest edges of everything we can see. This is not just philosophy, it has profound mathematical consequences, and it is here that we find a potential link to dark energy. When theorists apply the holographic principle to the entire cosmos, they find a compelling constraint. The total information content, or energy density, inside our observable universe cannot exceed what can be encoded on its boundary. This creates a natural limit, an infrared cutoff, tied directly to the size of the universe. As the cosmos expands, that boundary surface grows, and the maximum allowed energy density within it decreases. Remarkably, when you calculate what that maximum density should be today, based on the current size of our observable universe, you get a number. And that number is incredibly close to the tiny, observed value of the dark energy density. This is theory number 6. Dark energy is not some arbitrary constant slapped into Einstein's equations. It is a necessary consequence of living in a holographic universe. The energy of the vacuum is not a free parameter. It is fixed by the cosmic horizon, the ultimate screen on which reality is projected. This offers a breathtaking solution to the vacuum catastrophe, that monstrous 120 order of magnitude mismatch. In a holographic framework, you do not sum up all the frantic quantum fluctuations in the volume of space. That calculation, which gives the impossibly large number, is fundamentally wrong because it treats space as a collection of independent, three-dimensional degrees of freedom. But if the holographic principle is correct, those degrees of freedom are far fewer. They live on the boundary. The true vacuum energy is set by the universe's scale, not by the sum of every possible quantum jitter within it. It is as if we were trying to calculate the data on a high-definition movie by counting every molecule in the theater, when all the data is actually on the hard drive in the projection booth. The holographic principle provides a natural, elegant reason why dark energy is so unfathomably small yet not zero. It is tied to the sheer vastness of the cosmos. As the universe expands, the dark energy density will slowly dilute, not because the energy is changing, but because the holographic screen is getting larger. This theory moves the mystery from a question of substance to a question of structure. We are not asking what dark energy is made of, but what kind of universe we live in. Are we three-dimensional beings, or are we shadows on a distant two-dimensional wall, watching our own projected story unfold? The answer could rewrite not just cosmology, but the very meaning of existence. Phase transitions are not just for water turning to ice. They are fundamental shifts in the state of the universe itself. Theory 7 suggests our cosmos has recently undergone one of these profound transformations. This idea is called vacuum metamorphosis. It proposes that the vacuum of space is not a passive backdrop, but an active medium that can change its very nature, like water suddenly deciding to become steam. The trigger for this cosmic shift is a specific kind of scalar field, similar in concept to the quintessence field, but with a crucial difference. This field is coupled to gravity itself. Its behavior is tied to the curvature of spacetime. In the early, dense universe, spacetime was highly curved. The field was effectively trapped in a high-energy state, like a ball resting at the top of a hill. In this state, its influence was minimal, but as the universe expanded and thinned out, the curvature of spacetime gradually decreased. This was like the ground beneath the ball slowly sinking. Eventually, the universe reached a critical point, a specific threshold of low curvature. At that moment, the scalar field reached its critical mass. The hill flattened and the ball began to roll. The field underwent a spontaneous phase transition, tumbling down to a new, stable minimum of energy. This was not a minor adjustment. It was a fundamental change in the vacuum's properties, a metamorphosis of empty space. In its new state, the vacuum itself acquired a constant, repulsive energy density. The universe, in essence, clicked into a new gear. The phase transition did not add a new force from outside, it changed the rules of the game from within. The properties of the vacuum itself were rewritten, initiating the era of accelerated expansion we observe today. What makes this theory so compelling is its testable precision. Unlike the cosmological constant, which is a simple, unchanging number, vacuum metamorphosis makes a specific prediction about how the expansion rate of the universe, the Hubble parameter, has changed over cosmic time. It predicts a distinct timeline. For most of cosmic history, the expansion decelerated under the pull of matter and radiation, just as in the Standard Model. Then, at a specific redshift corresponding to when the universe was roughly half its current size, the phase transition occurred. The expansion rate would have made a subtle but detectable shift before settling into its current accelerating state. This creates a unique signature in the data, a kink in the curve of the universe's expansion history. Astronomers can hunt for this signature by measuring the distances to extremely bright supernova, the distribution of galaxies across vast surveys, and the subtle wrinkles in the cosmic microwave background. Finding that precise kink would be a smoking gun for vacuum metamorphosis, distinguishing it from the bland, featureless prediction of a simple cosmological constant. It transforms dark energy from a static fact into a dynamic event, a chapter in the universe's biography. We are left wondering, did we just happen to emerge in the cosmic epoch immediately following one of reality's great upgrades? The holographic universe and cosmic phase transitions push at the boundaries of known physics, but what if the answer lies in rewriting the rulebook for energy itself? Theory 8 ventures into this territory with a concept known as K-essence. Like its cousin quintessence, K-essence is a dynamical scalar field, a kind of cosmic fluid that fills all of space. But there is a crucial, game-changing twist. In standard physics, whether for a rolling ball or a vibrating string, the kinetic energy, the energy of motion, is simple and proportional to the square of its speed. For K-essence, this rule is broken. Its kinetic energy is described by a non-standard, more complex mathematical term. Think of it like this: ordinary kinetic energy is like the push you feel from a steady wind. The kinetic energy of a K-essence field is like the chaotic, unpredictable buffeting of a hurricane. This fundamental change in its very nature gives it extraordinary properties. In most fields, the potential energy, the energy stored in its configuration, is the dominant player. But for K-essence, it is this bizarre kinetic term that takes center stage. The field's frantic, non-standard motion becomes the primary source of its cosmic influence. This kinetic dominance leads to a remarkable and unique ability. Recall the phantom divide, that fateful line at an equation of state of -1, which phantom energy crosses to bring about the big rip. Most dynamical models, like quintessence, cannot cross this line. They are forever stuck on one side or the other. K-essence, however, has the mathematical freedom to do just that. Its unusual kinetic structure allows it to evolve from a state behaving like ordinary quintessence to one that mimics phantom energy, potentially crossing that phantom divide during the universe's history. This means a universe with K-essence could, in principle, start with a gentle acceleration, only to have that acceleration ramp up into a phantom-like phase later on, all driven by the changing dynamics of a single, strange field. So where does such a bizarre idea come from? Its origins are deeply rooted in the quest for a theory of everything. K-essence models naturally emerge from the dense mathematics of string theory and from attempts to describe the very early universe, like in some models of inflation. They are not invented arbitrarily to explain dark energy. They appear as plausible outcomes of our most advanced theoretical frameworks. This gives them a compelling pedigree. Furthermore, K-essence offers a clever solution to a major philosophical problem in cosmology: fine-tuning. Why is the dark energy density today so incredibly small compared to natural particle physics scales? Quintessence often requires its initial conditions to be set with exquisite, unnatural precision, like balancing a pencil on its tip at the beginning of time. K-essence can avoid this through what physicists call tracker solutions. Imagine a wide river with many possible starting points along its bank. A tracker solution is like a powerful current in the center of that river. No matter where you start, whether you throw your raft in near one shore or the other, the current will eventually pull you into the main flow. A K-essence field with tracker behavior works similarly. Its evolution over cosmic time is largely independent of its initial conditions. A vast range of starting values will all converge or track onto the same evolutionary path that leads to the small, dominant dark energy we see today. The universe, in this view, has a kind of cosmic attractor, a destiny built into the unusual physics of this field that naturally guides it to our current accelerated epoch without requiring miraculous fine-tuning at the dawn of time. It is a theory that combines exotic origins with a practical elegance, suggesting that the engine of our expansion may be a relic of the universe's most fundamental laws, finally settling into its dominant role after tracking its path for billions of years. String theory paints a universe of unimaginable depth, not in light years but in dimensions. Beyond the familiar 3 dimensions of space and 1 of time, it whispers of 6 or 7 more, curled up into sizes smaller than a subatomic particle. But one radical interpretation of this framework gives those extra dimensions a starring role in our cosmic drama. This is Theory 9, Brainworld Cosmology. Picture our entire observable universe, all its galaxies, stars, and planets, not as an island floating in a 3-dimensional void, but as a 3-dimensional sheet, a membrane, or simply a brain. This brane exists within a much larger, higher dimensional space called the bulk. We are like characters living on the vast, flat surface of a page, completely unaware of the immense volume of the book that page is part of. All the forces and particles we know, like light and matter, are stuck to our brain. They are like ink on the page, unable to leave its surface, but gravity, according to this idea, is different. It is the one force that can leak out, seeping off our brain and into the higher dimensional bulk. This leakage has a profound consequence. On our brain, gravity would appear weaker over very large distances because some of its influence is dissipating into the extra dimensions. This weakening could perfectly mimic the effects of a repulsive dark energy. As two galaxies grow very far apart, the gravitational attraction between them would diminish faster than expected in a purely four-dimensional universe, creating the illusion of an extra push driving them apart. But the story gets even more intriguing when we introduce other branes. What if our universe is not the only sheet in the cosmic book? Other three-dimensional branes could be floating in the bulk, parallel to our own, each hosting its own separate universe with its own laws of physics, utterly invisible to us because light cannot cross the gap. Yet gravity can. The subtle gravitational pull, or more likely, a repulsive interaction between our brain and a nearby parallel brane in the bulk could be the true source of dark energy. Imagine two sheets of paper suspended close together in a gentle breeze. They would exert a faint pressure on each other, a force that depends on their separation. If that separation is changing over cosmic time, the force would change with it. This provides a dynamic, elegant explanation rooted not in a mysterious fluid, but in the fundamental geometry of higher dimensional space. The energy driving the acceleration of our universe could be the shadow of a neighboring reality, a ghostly tug from a world we can never see. While the mathematics is formidable, the core idea is a breathtaking shift in perspective. Dark energy may not be a thing within our universe, but a signal of the universe's true place in a far grander, hidden architecture. Our accelerating expansion might simply be the gentle sway of our cosmic membrane in an unseen sea of dimensions. The search for dark energy's origin confronts a question that borders on philosophy. Why does this force have the precise, incredibly tiny value it does? One answer is as unsettling as it is simple. Perhaps there is no deeper reason. Theory 10, the anthropic principle, suggests the value of dark energy is not written into the fundamental laws of physics, but is instead a consequence of our own existence. We observe this specific number because in universes with any other value, we would not be here to observe anything at all. This is not an explanation from equations, but from selection. The idea gains traction from a startling prediction of string theory, the concept of the cosmic landscape. String theory does not yield a single, unique universe with one set of constants. Instead, its mathematics describe a vast, perhaps infinite, multiverse. Each universe within this multiverse corresponds to a different stable configuration, a different valley in an unimaginably complex energy landscape. In each of these valleys, the laws of physics are different. The strength of gravity, the mass of electrons, and crucially, the value of the cosmological constant or dark energy are all set randomly. Most of these universes are sterile, lifeless voids. If dark energy were even slightly stronger than what we measure, its repulsive push would have overwhelmed gravity in the universe's infancy. Matter would never have clumped together. Galaxies, stars, and planets would never have formed. The cosmos would be a featureless, expanding fog devoid of any structure. Conversely, if dark energy were much weaker or negative, gravity would have dominated completely. The universe might have collapsed back in on itself in a big crunch long before complex chemistry, let alone life, could arise. We find ourselves in a universe with a dark energy value that seems fine-tuned, not for perfection but for possibility. It is a Goldilocks value, just right to allow a long period of matter-dominated growth for galaxy formation, followed by a gentle acceleration that begins only after life has had billions of years to emerge. From the anthropic viewpoint, this is no cosmic coincidence. It is a statistical inevitability. Countless barren universes exist where the numbers do not allow for observers. We, by necessity, must find ourselves in one of the rare habitable ones. The controversy is profound. To many scientists, this feels like giving up on a fundamental explanation, replacing physics with a tautology. Yet its proponents argue it is simply applying the rules of probability to a multiverse that our best theories already imply. The anthropic principle does not tell us why dark energy exists, but it offers a stark reason why we measure the specific value we do. In the grand cosmic lottery, we hold the only possible winning ticket. The smooth cosmic background is a beautiful lie. Our maps of the universe show a vast, uniform sea of radiation, leading us to model the cosmos as a perfectly smooth fluid expanding evenly in all directions. But look closer, and that smoothness shatters into a breathtaking tapestry of extremes. Dense knots of galaxies are woven into vast filaments, which border cavernous voids billions of light years across, nearly empty of matter. This is the true, lumpy face of our universe. Theory 11 asks a radical question: what if we have been averaging things out incorrectly? The idea is called backreaction from inhomogeneities. It challenges the very foundation of how we interpret cosmic expansion, suggesting that dark energy might be a grand illusion born from our oversimplified math. In Einstein's equations, the curvature of spacetime tells matter how to move, and the distribution of matter tells spacetime how to curve. It is a dynamic, two-way street. In a perfectly smooth universe, this is straightforward. But in our real, clumpy cosmos, the relationship becomes fiendishly complex. The intense gravity within galaxy clusters curves spacetime dramatically in those regions. The near absence of gravity in the titanic voids also curves spacetime, but in a different way. When cosmologists calculate the average expansion rate of the universe, the standard approach is to take this lumpy matter distribution, smooth it all out into a uniform groove, plug that average density into Einstein's equations, and solve. Proponents of backreaction argue this smoothing step is not mathematically innocent. By averaging first and then applying the equations, we might be getting the answer wrong. The correct approach, they insist, is to apply Einstein's equations to the real, lumpy universe first. Calculate how every cluster and every void individually affects local expansion, and only then average the results. The difference is not just academic. The gravitational pull of dense clusters slows down expansion in their vicinity. The underdense voids, however, have the opposite effect. With so little matter to provide gravitational pull, space within these voids wants to expand faster. As the universe ages, matter flows from the voids into the filaments and clusters, making the voids ever larger and emptier. Their contribution to the overall expansion grows. The backreaction hypothesis proposes that when you properly account for this growing contrast, the average expansion rate you get from a lumpy universe is faster than the rate you would predict from a naive, smooth model. From our vantage point, making measurements across billions of light years that inevitably cut through both clusters and voids, this extra kick in the averaged expansion could look exactly like an accelerating universe driven by dark energy. In this view, there is no mysterious energy. There is only the complex collective gravity of a universe that is not smooth, acting in a way our simplified models fail to capture. It is a cosmic sleight of hand performed by structure itself. The debate around this idea is fierce. Critics point out that for backreaction to produce the observed acceleration, the effect would need to be enormous, and detailed simulations of cosmic structure formation have so far not shown such a large signal. The consensus remains that while inhomogeneities do influence the expansion in subtle ways, they are likely not powerful enough to fully mimic dark energy. Yet the theory stands as a crucial reminder, a testament to the complexity of the cosmos. It forces us to ask whether we are being fooled by our own simplifying assumptions, mistaking the intricate dance of a structured universe for the push of a phantom force. Einstein's equations are a symphony of 10 interwoven parts, describing the dynamic relationship between matter and the curvature of spacetime in all its complexity. But what if this beautiful machinery has a redundant part, a hidden cog that does nothing but complicate the tune? Theory 12, unimodular gravity, proposes we remove that cog to hear a simpler, perhaps more revealing melody. The technical heart of this idea lies in a mathematical constraint. In standard general relativity, the metric tensor, which defines distances and intervals in spacetime, has 10 independent components. Unimodular gravity imposes a strict condition on this metric, fixing its determinant to a constant value, typically -1. In simpler terms, it restricts the mathematical description of spacetime volume. You can still bend and stretch spacetime in this framework, twist it with gravity, and expand it with the cosmos, but you cannot arbitrarily change the fundamental unit of four-dimensional volume. This might seem like a minor technical tweak, but its philosophical and physical consequences are profound. By imposing this constraint, the equations of gravity simplify. Crucially, the famous cosmological constant term, that lambda that Einstein inserted and later discarded, does not appear as a fundamental parameter in the original equations. It is not something you put in by hand. Instead, when you solve the constrained equations of unimodular gravity, the cosmological constant emerges naturally as an integration constant. What does that mean? Think of it like solving a puzzle. In standard physics, you are given the puzzle box with a picture of the cosmological constant already on it, and you have to fit the pieces to match. In unimodular gravity, you are given the puzzle pieces without the box. As you assemble them based on the new rules, a specific image appears in the completed puzzle. That image is the cosmological constant. It is not an input, it is an output, a consequence of how you put the universe together given the unimodular constraint. This reframing offers a tantalizing solution to the fine-tuning problem. If lambda is a fundamental parameter, why is it so absurdly small? It looks like a number chosen with miraculous precision. But if it is an integration constant, its value is set by the initial conditions of the universe, by the boundary conditions of the puzzle. In the vast landscape of all possible universes that obey unimodular gravity, ours simply ended up with this particular constant. It did not need to be fine-tuned at the level of fundamental law. It just is what it is, a historical accident of cosmic birth. The value could even, in principle, be zero. The fact that it is not zero but a tiny positive number might then tell us something specific about how our universe began, rather than pointing to a mysterious, unexplained force woven into reality's fabric. While the predictions of unimodular gravity are, in many respects, identical to standard general relativity for most phenomena, this shift in perspective is powerful. It transforms dark energy from a mysterious actor in the play of physics into a piece of the stage itself, a set piece determined when the cosmic curtain first rose. It suggests that the engine of our acceleration might not be a substance or a field, but a silent footnote in the geometry of creation, a number waiting to be read once we learn the true language of spacetime. But what if the most sacred constant in all of physics is not constant at all? This is the audacious premise of Theory 13, the time-varying speed of light. For over a century, the speed of light in a vacuum, denoted by the letter c, has been the universe's ultimate speed limit and a cornerstone of relativity. It is woven into the fabric of spacetime itself. To suggest it changes is to pull at a thread that could unravel our entire understanding of reality. Yet some theorists propose that in the fiery first moments after the Big Bang, the speed of light was not 300,000 kilometers per second. It was vastly higher, perhaps infinite, and it has been slowing down ever since. This radical change is not a minor tweak. It is a complete reworking of cosmic history with the power to solve some of our deepest puzzles. Consider the horizon problem. The cosmic microwave background, the oldest light we can see, shows a nearly identical temperature in all directions. But in the standard model, these distant regions of the early universe were too far apart for light, traveling at a constant speed, to have ever connected them and equalized their temperature. They were causally disconnected, like strangers in separate rooms who somehow ended up wearing the exact same outfit. The leading solution is cosmic inflation, a period of fantastically rapid expansion that smoothed everything out. But a varying speed of light offers an alternative. If light traveled infinitely fast in the universe's infancy, then every corner of the cosmos was in instant contact. Information and heat could zip across the entire embryonic universe in no time at all, perfectly explaining the uniform temperature we observe today without needing a separate inflationary epoch. The same logic solves the flatness problem, the mystery of why the geometry of our universe is so perfectly balanced between open and closed. A much higher speed of light in the past would have forced the universe to rapidly evolve toward this precise flat state. So how does this connect to dark energy? As the speed of light decreased over billions of years, it would have altered the fundamental relationship between energy, pressure, and the expansion of the universe. In the equations of cosmology, the speed of light appears in the link between the pressure of a substance and its contribution to the cosmic expansion rate. A decreasing c can effectively mimic the behavior of a fluid with negative pressure. From our perspective, measuring everything with today's slower, fixed speed of light, the cosmic expansion would appear to be accelerating. The change in this fundamental constant over time creates an illusion, a phantom acceleration we label as dark energy. In this view, the force tearing the cosmos apart is not a new form of energy, but a fading echo of a time when the rules of physics were profoundly different. The challenge, however, is monumental. Simply declaring that sea changes is not enough. You must rebuild physics from the ground up. In Einstein's relativity, the speed of light is not just a number, it is the conversion factor between space and time, the linchpin of causality. If it varies, you must specify what it is varying relative to. Time itself, some other, more fundamental clock. Crafting a self-consistent theory where the laws of physics, particularly electromagnetism and gravity, still work coherently with a changing sea is an immense hurdle. Most attempts require breaking Lorentz invariance, the foundational principle that the laws of physics are the same for all observers moving at constant speed. This is a step most physicists are extremely reluctant to take, as it threatens the very bedrock of modern physics. So while the varying speed of light presents a breathtakingly unified solution, tying together the early universe's mysteries with our accelerating present, it does so at a potentially catastrophic cost. Are we witnessing the afterglow of a fading universal constant, or is this idea a bridge too far, a solution that creates more profound problems than it solves? The answer lies in the faintest signals from the dawn of time, waiting to be decoded. Gravity has always been the anchor of our cosmic understanding, a fundamental force carved into the bedrock of physics. But what if that bedrock is an illusion? Theory 14, emergent gravity, proposes exactly that. Pioneered by physicist Eric Verland, this idea does not just tweak our laws, it uproots them, suggesting gravity is not fundamental at all. It is not a force transmitted by particles or a curvature in spacetime as Einstein taught us. Instead, gravity emerges, like the wetness of water or the temperature of a gas, from something far more basic, the quantum entanglement of information. To grasp this, picture the universe not as a collection of objects in space, but as a vast, interconnected network of information. At the quantum level, particles share information through entanglement, a ghostly link that connects them instantly across any distance. This entangled information has a property called entropy, a measure of disorder or hidden knowledge. Verland's radical leap was to propose that what we perceive as gravity is actually a consequence of changes in this quantum entanglement entropy. Imagine space as a holographic screen storing information in bits like the pixels on your phone. When a massive object like a star is present, it alters the arrangement of information on that screen, increasing the entropy. Nature, always tending toward higher entropy, responds by moving the screen in a way that brings the star and other objects closer together. This statistical tendency for entropy to increase manifests as an attractive force, gravity. It is not a pull, but a thermodynamic drift toward disorder. This entropic framework yields astonishing results. When Verland applied his equations to the scale of galaxies, he found they naturally produced an extra gravitational effect in their outer regions, precisely where stars orbit too fast for the visible matter present. This effect perfectly mimics the role of dark matter, but without invoking any unseen particles. The extra pull comes from the emergent gravitational response to the galaxy's entropy gradient, not from hidden mass. But the true shock came when the theory was applied to the cosmos as a whole. In the vast, nearly empty intergalactic voids where matter density is vanishingly small, Verland's equations predict that the emergent gravity law changes form. The usual inverse square law of attraction weakens, and a new, repulsive term appears in the equations. This term acts as a constant, uniform pressure pushing space apart. Remarkably, its calculated strength aligns almost exactly with the observed value of dark energy. In this view, dark energy is not a separate substance or a cosmological constant. It is the other side of the same coin, a signature of gravity's emergent nature in the cosmic void. The acceleration of the universe is not driven by phantom energy or a quintessence field, but is an inevitable thermodynamic consequence of how information is structured in the emptiest places. It suggests that the two greatest mysteries of cosmology, dark matter and dark energy, might be a single misunderstanding, a failure to see that gravity itself is a secondary effect, a story told by the quantum information woven into the fabric of space. The idea that empty space is alive with energy is not just theoretical speculation. We can see its ghostly fingerprint in a laboratory. This is the Casimir effect, a phenomenon that brings the quantum vacuum's restless energy into the realm of measurable reality. Picture two perfectly smooth, uncharged metal plates placed incredibly close together in a vacuum, separated by a gap smaller than the width of a human hair. In the quantum world, the space between those plates is not empty. It is filled with a sea of virtual particles, constantly flickering into and out of existence. These are not real particles in the usual sense, but temporary fluctuations permitted by the uncertainty principle, borrowing energy from the vacuum for fleeting moments. Each type of particle has its own spectrum of possible fluctuations, like notes on a piano. However, the metal plates impose a boundary condition. Only certain wavelengths of these virtual particles, specific notes, can fit between the plates. Outside the plates, all wavelengths are possible. This creates an imbalance. The pressure from the virtual particles pushing on the outside of the plates is slightly greater than the pressure from the more limited set of fluctuations pushing from the inside. The result, the plates are pushed together by an invisible force from seemingly nothing at all. We have measured this force, and it matches the predictions of quantum field theory perfectly. The Casimir effect is direct, tangible proof that the vacuum is not a passive nothingness. It is a roiling quantum foam brimming with transient energy. This brings us to Theory 15, the direct link between this zero-point energy and dark energy. If the vacuum between two metal plates has measurable energy, then the vacuum filling the entire universe must have an unimaginably vast amount of it. This is the zero-point energy of all quantum fields, the baseline hum of reality. Every point in space, according to our best physics, contains this energy. And according to Einstein, all forms of energy gravitate. They curve spacetime and influence the expansion of the cosmos. So here lies the heart of the catastrophe. When physicists attempt to calculate the total zero-point energy of the vacuum by summing up the contributions from every known quantum field, they get a number that is absurdly, catastrophically large. We are talking about an energy density that would cause the universe to expand with such violent force that galaxies, stars, and even atoms could never have formed. The cosmos would have ripped itself to pieces in an instant after the Big Bang. Yet we are here. The universe is not only intact, but its acceleration is gentle, a tiny, faint pressure compared to the theoretical hurricane. This is the cosmological constant problem in its starkest form. The Casimir effect proves the quantum vacuum has energy, but the universe behaves as if that energy is 120 orders of magnitude smaller than our calculations say it should be. It is the single largest discrepancy between theory and observation in all of science. So the core mystery every dark energy theory must solve is not merely what is pushing the universe apart. The deeper question is, why is the push so inconceivably weak? Why does the furious quantum cacophony of the vacuum seem to whisper rather than scream when it comes to gravity? Any successful theory must either explain why our calculation of the vacuum energy is wrong, or reveal the mechanism that shields gravity from its overwhelming power, leaving behind only the faintest echo we call dark energy. The vacuum catastrophe presents a paradox of detection, where the energy we know exists is not the energy we see shaping the cosmos. But what if dark energy is not absent from our local universe, it is simply hiding in plain sight? This brings us to Theory 16, the symmetron field, a concept that introduces a cosmic game of hide and seek governed by the density of matter itself. The symmetron is a type of light scalar field, a cousin to quintessence, but with a brilliant and specific trick. It couples to ordinary matter, meaning its behavior and strength are directly tied to the density of the material environment around it. In regions of high density, like within our galaxy, inside our solar system, or even here on Earth, the symmetron field is effectively screened. Imagine it as a chameleon pressed against a bright, colorful tapestry. The intense presence of matter overwhelms the field, forcing it into a symmetrical state where it has zero value and exerts no long-range force. It becomes invisible to local experiments, perfectly camouflaged against the dense backdrop of stars and planets. This screening mechanism is crucial because it explains why we do not feel any strange, repulsive push from dark energy in our daily lives or in the precise orbits of planets. The field is switched off by the sheer amount of matter surrounding us, but the cosmos is not uniformly crowded. Between the great filaments of galaxies lie the immense cosmic voids, regions of staggering emptiness that can span hundreds of millions of light years. In these vast, low-density deserts, the environment changes dramatically. With the suffocating pressure of matter lifted, the symmetron field unscreens. Like that chameleon finally moving onto a blank gray wall, its true colors show. The symmetry breaks and the field acquires a non-zero value. In this unscreened state, it activates with a long range, filling the void with a constant, repulsive energy that pushes the boundaries of these empty regions outward. Since the universe is mostly void, this collective repulsion from countless unscreened symmetron fields across all the cosmic deserts adds up to a global effect, driving the accelerated expansion we measure from our vantage point. The elegance is profound. The symmetron field is not a uniform energy blanket, but a responsive entity, its influence dictated by the architecture of the universe itself. It is dark in galaxies not because it is weak, but because it is suppressed by matter. It is energetic in voids because emptiness allows it to awaken. This provides a natural explanation for the most puzzling aspect of dark energy, why its effects are undetectable in our local, dense neighborhood yet dominate the cosmos at large. We are simply living in a region where the mystery has been temporarily silenced, While all around us, in the great nothingness between galaxies, the true force is stretching the fabric of reality. Gravity is the only fundamental force without a known particle carrier. We have photons for light, gluons for the strong force, and W and Z bosons for the weak force. For gravity, the hypothetical messenger is the graviton, a massless particle that would travel at the speed of light and mediate the curvature of spacetime. But what if that assumption is wrong? What if the graviton has a tiny, almost imperceptible mass? This is the radical proposal of Theory 17, massive gravity. For decades, the idea was considered a theoretical dead end. The mathematics of giving the graviton a mass in a manner consistent with Einstein's relativity seemed to inevitably produce ghostly instabilities. These ghosts were not just mathematical quirks, they were predictions of negative probabilities and runaway energies that would cause the universe to unravel instantly. Any theory that predicted such nonsense was clearly flawed, and massive gravity was relegated to the sidelines. That changed dramatically in the early 2010s with a breakthrough by physicists Claudia de Rham, Gregory Gabadadze, and Andrew Tolley. Their theory, known as DRGT massive gravity, finally tamed the ghosts. They constructed a complex but self-consistent mathematical framework where the graviton could have a tiny mass without triggering cosmic catastrophe. It was a monumental achievement, reviving an entire field of study. So what happens if the graviton is not massless? In Einstein's general relativity, a massless graviton leads to a force that obeys the famous inverse square law perfectly over all distances. But a massive graviton changes the story. It introduces a new scale into the universe related to its Compton wavelength, the distance over which its influence can be felt. On small scales, like within our solar system or a galaxy, the mass would be so minuscule that gravity would behave exactly as we observe, passing all our precision tests. The modifications would only kick in on the largest cosmic scales, distances comparable to the size of the observable universe itself. On these vast scales, the massive graviton's influence would weaken and alter. The force of gravity would effectively get a haircut, its long-range pull diminishing faster than the inverse square law predicts. From our perspective, measuring the tug between superclusters of galaxies, this weakening would look exactly like a repulsive effect. The cosmos would appear to be expanding faster than gravity alone can account for, perfectly mimicking the presence of dark energy. In this view, the acceleration is not driven by a new energy form, but by gravity itself growing feeble on the grandest stages, its signal fading because its messenger particle is not quite massless. The hunt is now on for evidence. The most promising test comes from gravitational waves, the ripples in spacetime from colliding black holes and neutron stars. A massless graviton, like the photon, must travel at the speed of light. A massive graviton, however, would travel slightly slower, and its speed would depend on its wavelength. More importantly, the way it propagates through the cosmos would subtly alter the pattern of gravitational waves we detect from distant cataclysms. By comparing the arrival times of gravitational waves with light from the same event, like a neutron-star merger, scientists can probe the graviton's mass. If gravitational waves consistently arrive with even a tiny delay compared to light, it would be a smoking gun for a massive graviton. Current observations from LIGO and Virgo have already placed incredibly tight constraints, suggesting that if the graviton has a mass, it is less than 1/10,000,000th of a billionth of a billionth of a billionth of the mass of an electron. The search continues, with every new cosmic crash offering a chance to weigh the ghostly particle of gravity and perhaps solve the dark energy puzzle by finally completing the family portrait of the universe's fundamental forces. Supersymmetry was physics' great hope for a perfectly balanced universe. This elegant extension of the standard model, often called SUSY, proposes a profound symmetry at nature's most fundamental level. For every known particle of matter, like quarks and electrons, there should exist a superpartner, a boson. For every force carrying boson, like the photon, there should be a fermionic superpartner. The electron gets a selectron, the quark gets a squark, the photon gets a photino. In this unbroken, pristine state of supersymmetry, the universe achieves a kind of mathematical perfection. The frantic quantum jitters of a particle and its superpartner are opposites in a key way. One contributes a positive amount to the vacuum energy, the other contributes an equal and opposite negative amount. Their combined effect is a perfect cancellation, a cosmic zero. The vacuum energy problem vanishes because the relentless buzz of the quantum foam is silenced by this exquisite partnership. This is Theory 18, the cosmological constant emerging from broken symmetry. Our universe, however, is clearly not supersymmetric. We do not see selectrons or photinos with the same mass as their familiar partners. If they existed at those low masses, our particle colliders would have created them by now. This means supersymmetry, if it is a truth of nature, must be broken. It was a perfect symmetry only at the unimaginably high energies of the early universe. As the cosmos cooled and expanded, that symmetry shattered. The superpartners gained enormous masses, far too heavy for our current colliders to detect, leaving behind the relatively light particles of the standard model we know today. But when a perfect symmetry breaks, it does not leave a perfect void. The cancellation of vacuum energy is no longer exact. The delicate balance between particle and superpartner is upset because their masses are now vastly different. Their quantum fluctuations no longer mirror each other perfectly. The result is a tiny mismatch, a minuscule leftover energy from the broken symmetry. This residual energy, theorists suggest, could be the cosmological constant we observe as dark energy. Its value is not the unfathomably large number from raw quantum field theory, but a small, positive remnant of a grand symmetry that once was. It is the faintest echo of a more perfect, balanced cosmos, a whisper of supersymmetry imprinted on the accelerating expansion of space. The beauty of this idea is its explanatory power. It ties the largest-scale mystery of cosmology directly to one of the deepest puzzles in particle physics. Yet it comes with a heavy price. To produce a cosmological constant as small as the one we measure, the breaking of supersymmetry must be exquisitely tuned. The masses of the superpartners must be arranged with a precision that some argue reintroduces the very fine-tuning problem Sussy was meant to solve. Furthermore, the simplest versions of supersymmetry predict a cosmological constant that is negative, not positive, which would cause the universe to collapse, not accelerate. More complex models can yield a positive value, but the quest for a natural, untuned explanation remains. The hunt for supersymmetry at the Large Hadron Collider continues, not just for dark energy, but for a host of other reasons. Finding any superpartner would revolutionize physics and offer a potential pathway to understanding why our vacuum hums with this specific, gentle energy. Until then, it remains a breathtaking possibility that the force pushing galaxies apart is the cosmic signature of a lost symmetry, a broken mirror reflecting a more perfect version of reality. A particle with imaginary mass sounds like a contradiction, a mathematical impossibility. Yet within the elegant equations of string theory, such an entity not only exists but plays a starring role in one of its most dramatic processes. This is the tachyon, a hypothetical particle whose very definition defies our intuition. In ordinary physics, mass is a positive number. It represents inertia, the resistance to acceleration. A tachyon's mass, however, is described by an imaginary number, a concept involving the square root of -1. This bizarre property gives it a behavior that seems pulled from science fiction. If a tachyon could exist as a real, observable particle, it would always travel faster than light, its speed increasing as it loses energy. More importantly for our story, its presence is a universal sign of instability. In string theory, the appearance of a tachyon in a system signals that the configuration is unstable. poised to decay into something more stable, like a pencil balanced perfectly on its tip. This brings us to Theory 19, the tachyonic condensate. The stage for this cosmic drama is not empty space, but a specific object in string theory called a D-brane. Think of a D-brane as a multidimensional membrane upon which the endpoints of strings are anchored. They are like cosmic canvases, and our entire universe could be embedded on one. Now imagine an unstable D-brane, a high-energy, excited state of this canvas. The theory tells us that such a brane will have a tachyonic field living on it. This field is not a particle zipping around, but a kind of energy landscape, like a hill. The tachyon represents the field being perched precariously at the top of that hill. This is an unsustainable situation. The system must decay. The tachyonic field begins to roll down its potential hill, a process called condensation. As it rolls, it releases energy, and the unstable D-brane decays, shedding its excited state. The field eventually settles into a stable valley at the bottom of the hill. But here is the crucial twist. At the bottom of this valley, the field's energy is not zero. It has a positive, constant value, and because of the unique shape of this tachyonic potential in string theory, this stable state possesses a strong negative pressure. This negative pressure, as we have learned, is the key ingredient for cosmic repulsion. In this specific string theory picture, the dark energy permeating our universe could be the aftermath of a grand decay. It is the stable, low-energy residue left over after an unstable D-brane. Perhaps the very fabric of our early cosmos underwent a tachyonic condensation. Our accelerating expansion is not the push of a new force, but the gentle, leftover pressure from a cosmic stabilization event that occurred in the deepest past. This theory is fascinating because it provides a concrete particle physics mechanism for a quintessence-like field. It is not just a mathematical abstraction, it is a specific outcome from one of our most ambitious theories of everything. The tachyonic condensate tells a story where dark energy is a chapter in the life cycle of the universe's fundamental structure, the calm after a storm of dimensional decay, a permanent signature of the cosmos finding its footing. The holographic principle offers a radical framework, but how does it translate into a precise, testable prediction for dark energy? One compelling answer emerges from the mathematics of curvature itself. This is Theory 20, the Ricci dark energy model. It proposes a specific and elegant holographic recipe where the dark energy density at any point in cosmic history is directly proportional to the average Ricci scalar curvature of the universe at that time. The Ricci scalar is not a random choice. In Einstein's equations, it is the simplest measure of how spacetime is curved by the presence of matter and energy. It is a cosmic average, a single number that tells you whether space on the largest scales is positively curved like a sphere, negatively curved like a saddle, or perfectly flat. In this model, the mysterious infrared cutoff, that ultimate screen where holographic information is stored, is not tied to the size of the universe in a simple way. Instead, it is tied to its curvature. The idea is that the maximum amount of information relevant to a region is limited by its Ricci curvature. This is a profound link because curvature is caused by what is inside a region. It is a direct consequence of causality. The curvature here is determined by the matter and energy that have had time to influence this point through the finite speed of light. This naturally incorporates causality into the holographic principle, ensuring that the dark energy we calculate is based only on causes that could have actually affected our region of spacetime. So, what does this model predict? As the universe evolves from a dense, hot, highly curved state into a vast, dilute, nearly flat expanse, the Ricci scalar decreases. Since the dark energy density is proportional to this curvature, it too must evolve. In the early universe, when matter was dominant and curvature was high, the Ricci dark energy would have been a small component, overshadowed by radiation and matter. But as expansion diluted matter, the curvature dropped, and the dark energy density, while also decreasing, did so at a slower rate. Eventually, it caught up and surpassed the density of matter, initiating acceleration. This gives the model a dynamic character. Unlike the rigid cosmological constant, the equation of state parameter in the Ricci model is not fixed at -1. It starts in the quintessence regime greater than -1 and can evolve across that phantom divide to values less than -1 in the future, potentially hinting at a phantom fate without requiring a truly phantom field. When astronomers test this specific prediction against the gold standard data, from the distances of Type Ia supernova to the detailed power spectrum of the cosmic microwave background, they find something remarkable. The Ricci dark energy model fits the observations as well as, and in some analyses even slightly better than, the standard cosmological constant model. It provides a natural explanation for why dark energy became dominant when it did, linking it directly to the universe's transition from a high curvature to a low curvature state. Here, dark energy is not an arbitrary add-on. It is a geometric response, a holographic echo of the universe's own changing shape, written in the language of curvature that gravity itself can read. The holographic principle offers many paths to the same profound truth. Another, even more minimalist route ties the fate of the cosmos directly to the ticking of a cosmic clock. This is Theory 21, Agiographic Dark Energy. It proposes a breathtakingly simple holographic recipe that the dark energy density is inversely proportional to the square of the age of the universe itself. In this view, the fundamental infrared cutoff, the ultimate pixel size of reality's screen, is not space but time. The principle is called agiographic from the Greek word for time because it asserts there is a fundamental, indivisible unit of time, a chronon, just as there is a fundamental, indivisible unit of distance, the Planck length. You cannot measure a duration shorter than this chronon, just as you cannot measure a length smaller than the Planck scale. This means the age of the universe, measured in these fundamental time units, provides the most natural and absolute limit for how much information can be processed or stored within the cosmic horizon. Think of the universe as a computer with a finite processor speed. The total number of operations it can have performed since the Big Bang is limited by its age. This computational limit, in turn, caps the energy density allowed within it. As the universe gets older, this maximum allowed density decreases. The formula is stark. The dark energy density equals a constant divided by the age of the universe squared. When the universe was young, its age was small, so the allowed dark energy density was enormous. But that enormous energy was utterly dominated by the even more colossal densities of radiation and matter in the fiery early cosmos. As the universe aged, its matter and radiation diluted away with expansion, following their own mathematical laws. Meanwhile, the agiographic dark energy density also decreased, but at a different, slower rate dictated by the aging clock. About 5 billion years ago, the two declining lines crossed. The universe, now mature and much older, had an agiographic energy density that finally surpassed the dwindling density of matter. The era of acceleration began, not because a new force switched on, but because the universe reached a certain birthday. This model stands in elegant contrast to its holographic cousin, the Ricci model. The Ricci model is spatial and causal, its dark energy tied to the curvature caused by the matter within our cosmic horizon. It is about what is here. The agiographic model is temporal and absolute, its dark energy tied to the sheer passage of time since creation. It is about how long this has been going on. One is rooted in the geometry of space, the other in the inevitability of time. The agiographic idea is philosophically compelling, reducing one of cosmology's greatest mysteries to a simple function of cosmic aging. However, this very simplicity places it under intense observational pressure. the model makes a very specific prediction for how the equation of state of dark energy should behave over cosmic history. When astronomers compare this prediction to the precise data from supernova, the cosmic microwave background, and the large-scale structure of galaxies, they find a noticeable tension. The pure hagiographic model, in its original form, does not fit the data as well as the cosmological constant or the Rick-side dark energy model. It tends to predict an acceleration that starts a bit too late or evolves in a way that clashes with our detailed maps of the universe's expansion history. This has led theorists to propose modified versions, like allowing the fundamental time unit to differ from the Planck time, or introducing interactions between the hagiographic dark energy and matter. Yet these adjustments can feel like moving away from the elegant, minimalist heart of the idea. So the hagiographic model remains a beautiful and thought-provoking possibility, a stark reminder that time itself may be the ultimate architect of our accelerating fate. It challenges us to consider whether the universe's expansion is not driven by a what, but by a when. Every map of the cosmos reveals a startling truth: the universe is not a uniform soup. It is a web of dense clusters bordering cavernous voids. But what if our place on that map is not average? What if our entire observable universe, all 93 billion light-years of it we can see, is not a representative sample but lies inside one of those titanic voids? This is the radical premise of Theory 22, the void hypothesis. It proposes a breathtaking flip in perspective, that dark energy is a grand illusion born from a cosmic accident of location. Imagine the universe on the largest scales is like a vast, gently rolling landscape of hills and valleys, where hills represent overdense regions and valleys represent underdense ones. The standard cosmological model assumes we are on a flat plane, giving us a true, average view of the whole. The void hypothesis suggests we are not on the plane, we are deep inside a valley, a staggeringly large underdense region billions of light-years across. From this privileged but biased vantage point, our measurements of cosmic expansion would be profoundly skewed. Here is why. According to general relativity, the expansion rate of the universe is not a single global number. It depends on the local density of matter. In an underdense void where gravity's pull is weaker, space expands faster than the true global average. Outside our void, in the denser hills of the cosmic landscape, the expansion is slower. Now picture us inside our fast-expanding bubble looking out. When we measure the distance to a supernova in a distant galaxy, we use its brightness as a standard candle. But the light from that supernova has traveled to us across a changing landscape. If that light spent most of its journey traveling through the faster expanding void we inhabit, its path would be stretched more than we would expect if we assumed a uniform, average universe. This extra stretching makes the supernova appear fainter and therefore farther away than our standard model predicts. When we plot many such distant supernovae, we see a pattern: they all look too faint. And the pattern perfectly mimics what we would see if the universe's expansion were accelerating due to dark energy. In this view, there is no mysterious repulsive force. There is only geometry and gravity, and we are sitting in an unusual place that distorts our cosmic survey. The acceleration is not real, it is apparent, a local mirage created by our residence in a cosmic valley. The appeal is immense. It eliminates the need for dark energy entirely, replacing it with a simple, if extraordinary, matter distribution. Yet this elegant idea collides with one of the most precise datasets in all of science, the cosmic microwave background. The CMB is the afterglow of the Big Bang, a snapshot of the infant universe when it was only 380,000 years old. Its temperature is nearly identical in every direction to about 1 part in 100,000. This incredible uniformity is a cornerstone of cosmology. For the void hypothesis to work, our gigantic underdense region must have been imprinted on the universe from its very beginning. We would need to be at the center of a spherical void that was already vast and underdense when the CMB light was emitted. This creates a devastating observational problem. If we are in such a void, the CMB light coming to us from different directions would have traveled through different densities. Light coming from the direction of the void center where we are would have traveled through the fastest expanding, most underdense region. Light coming from the edges of the void would have passed through slightly denser, slower expanding material. This would imprint a massive, glaring temperature variation across the sky, a hot spot in one direction and a cold spot in the opposite direction, centered perfectly on us. We see no such thing. The CMB is exquisitely isotropic. To explain its smoothness from inside a giant void, the model becomes incredibly contrived, requiring us to be almost exactly at the void's center to a precision that feels more miraculous than the fine-tuning of dark energy. It replaces one coincidence with another, far more severe one. Furthermore, detailed surveys of galaxy distributions and the integrated Sachs-Wolf effect, another subtle imprint on the CMB, have failed to find evidence for a void large enough and deep enough to explain the apparent acceleration. The universe, on the scales we can survey, looks statistically homogeneous. While the void hypothesis remains a fascinating intellectual exercise, a testament to questioning our most basic assumptions, it currently stands as a beautiful idea refuted by the cold, hard light from the dawn of time. Our place in the cosmos may not be special, and that very ordinariness might be the key to its greatest mystery. Two great cosmic shadows might be cast by a single, ghostly particle. This is the promise of Theory 23, dark energy from actions. To understand it, we must first meet the action, a hypothetical particle born not from cosmology, but from the heart of the atom. Deep within the nucleus, the strong nuclear force that binds quarks together has a puzzling symmetry. The equations allow for a violation of a combination of charge and parity, known as CP, which should make the neutron have a much larger electric dipole moment than it does. The fact that we do not see this violation is called the strong CP problem. The most elegant solution is the action, an ultra-light particle predicted to exist precisely to preserve this symmetry. It is a compelling candidate for dark matter, as vast numbers of these slow-moving, weakly interacting particles could fill galactic halos, but the action story does not end there. In the early universe, such a light scalar field would have been set into motion, oscillating back and forth in its potential like a cosmic pendulum. Initially, when the universe was young and dense, the field's oscillations were rapid and its energy density behaved like cold dark matter, clumping and providing gravitational scaffolding. However, as the cosmos expanded over billions of years, the pendulum's swing slowed. The field's oscillations became more gradual and its behavior began to change. In this late-time, slow-rolling phase, the action field can develop a strong negative pressure. It transitions from behaving like pressureless matter to acting like a smooth, repulsive energy fluid. This is the key. A specific class of very light action-like particles with masses fine-tuned to an almost unimaginably small value could have completed this transition only recently in cosmic history. Their oscillations have now slowed to a near standstill, and the field has effectively frozen, its constant energy density and negative pressure now dominating the cosmos and driving the accelerated expansion. In this elegant unification, the same field that once seeded the structure of galaxies now tears the intergalactic void apart. The action provides a potential bridge, a single entity whose changing role over cosmic time addresses both of our greatest mysteries. Its early oscillations account for dark matter, its late time freeze-out accounts for dark energy. This theory weaves a beautiful narrative from particle physics to the fate of the universe, suggesting that the two dominant yet invisible components of reality are not strangers, but different ages of the same fundamental substance. The challenge, as always, lies in the details. Can a single action field's properties be tuned to match the precise observed ratios of dark matter and dark energy? Experiments hunting for actions as dark matter, like atoms, are probing specific mass ranges, while cosmological observations constrain the field's dynamics. Finding an action would be a monumental discovery, but confirming it as the source of both shadows would be a revelation, showing us a universe where simplicity hides in the oscillations of a ghost. The mathematics of hiding a secret can be as ingenious as the secret itself. To shield a colossal vacuum energy from the universe, physicists constructed a theoretical Fab Four. These are not musicians, but four specific terms in a Lagrangian, the mathematical blueprint for a theory, named with a wink to the Beatles. John, Paul, George, and Ringo each represent a unique way for a special type of field, called a Galilean field, to interact with gravity and with itself. The goal of this quartet is not to eliminate the vacuum energy, but to disguise it, to prevent its overwhelming gravitational weight from crushing the cosmos. Imagine the vacuum energy as a monstrously heavy boulder sitting in the middle of a delicate glass museum. In standard physics, that boulder's weight would shatter the floor and collapse the building. The Fab Four theories are like a team of expert engineers who install a network of perfectly calibrated springs and counterweights beneath the floor. They distribute and cancel out the boulder's crushing force so effectively that the glass displays barely even tremble. The Galilean field is the mechanism of this cosmic engineering. It is a scalar field, but one with very special, non-standard derivative couplings. This means its influence depends not just on its value, but on how it changes across space and time, on its gradients and its rates of change. The John, Paul, George, and Ringo terms are mathematical expressions that cleverly combine these derivatives of the Galilean field with the curvature of spacetime itself. Their magic lies in a screening mechanism far more sophisticated than simple suppression. In regions of high curvature or high matter density, like near stars or within galaxies, the Galilean field activates powerfully. Its configuration automatically adjusts to exactly cancel out the gravitational effect of the underlying vacuum energy. The immense weight of the quantum vacuum is still there, but the Galilean field's interaction with gravity creates an equal and opposite push, a perfect balance that renders the vacuum energy gravitationally invisible. Local experiments and planetary orbits feel only the familiar pull of ordinary matter, completely unaware of the titanic forces being neutralized around them. But in the vast, low-density voids of intergalactic space, where space-time curvature is gentle, the screening weakens. The Galilean field's configuration changes. It can no longer fully cancel the vacuum energy's gravitational effect. A tiny fraction of that colossal underlying energy leaks through the screening mechanism. This residual, unscreened energy is what we perceive as the gentle, repulsive force of dark energy. In this breathtaking framework, the cosmological constant problem is solved not by making the vacuum energy small, but by explaining why it is so ghostly. The quantum vacuum's energy is as enormous as quantum field theory predicts, but the Fab Four and their Galilean field prevent almost all of it from curving spacetime. What we call dark energy is merely the 1 part in 10 to the 120th power that manages to seep through the cosmic filter in the emptiest places. It suggests we are not measuring the energy of the vacuum, but the exquisite imperfection of a hiding place that spans the entire universe. The laws of heat and energy may hold the key to the cosmos's expansion. Thermodynamics, the science of engines and ice melting, governs the flow of energy in every closed system, and there is no system more closed than the entire observable universe. Theory 25 proposes we stop searching for a substance called dark energy and instead view cosmic acceleration as an inevitable thermodynamic effect, a consequence of the universe's fundamental need to maximize entropy. To see how, we must first redefine the universe's boundary. In cosmology, we are not looking at the edge of a ball, but at the limit of causality. This is the cosmic event horizon, the farthest distance from which light will ever reach us in the infinite future due to the accelerating expansion. Nothing beyond that horizon can ever affect us, and we can never affect it. It is a one-way information barrier, much like the event horizon of a black hole. And just like a black hole horizon, this cosmic horizon has thermodynamic properties. It has entropy proportional to its area, and according to the groundbreaking work of physicists like Jacob Bekenstein and Stephen Hawking, it should also have a temperature. This is not a temperature like the heat of a star, but a subtle quantum effect called the Unruh temperature. An observer accelerating through empty space would perceive a warm bath of radiation where a stationary observer sees nothing. Because our cosmic horizon is fundamentally linked to acceleration, it too carries this ghostly thermal energy. Now apply the first law of thermodynamics, the principle of energy conservation, to this horizon. The law states that the change in energy of a system equals the heat added minus the work done by the system. Treat the horizon as the boundary of our cosmic system. The heat flow across this boundary is related to its temperature and the change in its entropy. The work done is the pressure of the cosmos times the change in volume as the universe expands. When you work through this thermodynamic equation, balancing heat, work, and entropy at the horizon, something remarkable emerges. The result is an equation that perfectly describes the acceleration of the universe. A term appears that looks exactly like a cosmological constant, a repulsive pressure driving expansion. In this view, dark energy is not a mysterious fluid we must discover. It is the thermodynamic force required to keep the cosmic books balanced, to ensure the first law is satisfied at the ultimate boundary of reality. The acceleration is what happens when the universe, as a thermodynamic system, naturally evolves toward a state of maximum entropy. It is an emergent phenomenon, a large-scale consequence of the statistical behavior of the fundamental degrees of freedom on the horizon. Much like the pressure of a gas emerges from the collective collisions of countless molecules. We are not being pushed apart by dark energy. We are witnessing the universe settling into its most probable, most disordered state. And the mathematics of that settling requires the fabric of space to stretch at an ever-increasing rate. This reframes the entire mystery. The question shifts from what dark energy is to why the cosmic horizon has the specific thermodynamic properties it does. The search moves from particle detectors to the profound links between information, gravity, and heat. Perhaps the engine of the cosmos is not a force at all, but the silent, inevitable ticking of the universe's thermodynamic clock. The promise of extra dimensions offers more than hidden worlds. It can rewrite the rules of gravity itself. This is Theory 26, the Diwali-Gabadad's Poroti model, a specific and elegant vision of a brain world where the mathematics yields a startling prediction, a universe that accelerates itself. Picture our familiar four-dimensional universe, three of space and one of time, as a membrane floating within a flat, infinite five-dimensional space called the bulk. In this DGP model, all the particles and forces of the standard model are confined to our brain, like characters painted on a canvas, but gravity is different. It is free to seep off our brain and propagate into the fifth dimension. This leakage is not constant, it is governed by a crossover scale, a critical distance. On small scales, like within our solar system, gravity behaves exactly as Einstein predicted, its force bending tightly to our brain. But on cosmic scales beyond this critical distance, gravity weakens significantly as its lines of force dissipate into the extra dimension. This modified force of attraction has a direct and profound consequence for the expansion of the universe. When cosmologists solved the equations of this model, they found two possible cosmic histories for our brain. One was the normal branch, which closely resembles the standard Big Bang model and requires a cosmological constant to explain acceleration. The other was far more exciting, the self-accelerating branch. In this solution, the very act of gravity leaking into the fifth dimension at large scales feeds back into the brain's expansion dynamics. The mathematics showed that the cosmic expansion on the brain would naturally accelerate at late times without any need for a cosmological constant, quintessence, or any other form of dark energy. The acceleration was self-generated, an emergent property of gravity's multidimensional escape. For a time, the DGP model was a beacon of hope. It provided a compelling, geometric alternative to dark energy, rooted in the elegant framework of extra dimensions. It made a clear, testable prediction for how the expansion rate of the universe should change over time, a specific curve for the Hubble parameter that differed from the cosmological constant. Astronomers raced to test it against the growing trove of supernova data, and crucially, against observations of the large-scale structure of the universe. The model's fate was sealed by a subtle but powerful effect known as integrated Sachs-Wolf. As cosmic structures like galaxy clusters grow, they create gravitational potential wells. When light from the cosmic microwave background passes through these evolving wells, it gains or loses a tiny amount of energy, leaving a specific imprint on the CMB's temperature map. The DGP model, with its particular modification of gravity, predicted a very strong integrated Sachs-Wolf signal. When scientists meticulously analyzed the data from the Wilkinson microwave anisotropy probe and later the Planck satellite, they found the signal was far weaker than the self-accelerating DGP model predicted. The universe's large-scale structure and the CMB were speaking with one voice, and they ruled out the simplest, most elegant version of this self-accelerating brain world. While the core idea remains influential, demonstrating how extra dimensions can dramatically alter cosmology, the specific promise of a self-accelerating universe without dark energy has faded under the harsh light of data. It stands as a monument to a beautiful road not taken, a reminder that even the most compelling geometry must ultimately bow to the evidence written in the ancient light of the cosmos. At the very foundation of reality, a limit is etched into the fabric of space and time. Quantum gravity, the long-sought union of general relativity and quantum mechanics, suggests that distances cannot be divided forever. There is a fundamental graininess to the cosmos, a smallest possible unit of length known as the Planck length, about 1.6 times 10 to the negative 35 meters. 100 billion times smaller than a proton. Beneath this scale, the very concepts of here and there lose their meaning. Our smooth, continuous equations of spacetime are an approximation, a useful fiction that breaks down at this ultimate frontier. Theory 27 proposes that dark energy is not an exotic substance, but a direct echo of this quantum gravitational grain. It is the price we pay for living in a universe where space itself is discrete. To understand how, we must look at the engine of cosmic expansion, the Friedmann equations. These are the specific solutions to Einstein's equations that describe how the universe expands based on its contents, matter, radiation, and any cosmological constant. They are classical, smooth, and continuous, assuming space is an infinitely divisible backdrop. But if spacetime has a fundamental pixel size, a minimal length, then these equations are incomplete. They are like trying to describe a digital photograph using only the mathematics of a continuous painting, missing the crucial fact of pixels. When physicists attempt to rewrite the Friedmann equations to account for this discreteness, to make them compatible with a quantized spacetime, new terms inevitably appear in the mathematics. These are correction terms, quantum gravitational tweaks that were negligible in the hot, dense early universe but grow in significance as space expands and thins out. One of the most compelling ways these corrections manifest is through a concept known as holographic dark energy, but with a specific twist tied to the infrared cutoff. Recall that holographic principles suggest the dark energy density is limited by the information content of a cosmic screen. If the fundamental pixel of that screen is the Planck area, then the total number of degrees of freedom is finite. Incorporating the minimal length directly into the cosmology equations leads to a specific formula where the dark energy density depends on the Planck length and the Hubble scale, the current rate of the universe's expansion. The result is a dynamic energy that naturally emerges from the geometry of a quantized cosmos. It is as if the universe, upon reaching a certain size and age, began to feel the granularity of its own construction. The acceleration we measure is the macroscopic symptom of spacetime's microscopic quantum structure, finally making its presence known on the largest scales. This idea transforms the cosmological constant from a mysterious input into a potentially calculable output. The tiny value of dark energy, that infamous 1 part in 10 to the 120th, might find its origin in the ratio of the Planck length squared to the square of the current horizon size of the universe. It is a number constructed from the fundamental scale of quantum gravity and the observational scale of our cosmic epoch. While still incredibly small, it is no longer an arbitrary parameter to be fine-tuned, but a number that could, in principle, be derived from first principles of a complete theory of quantum gravity, like loop quantum cosmology or certain string theory formulations. The acceleration is not driven by a ghost in the machine, but by the machine's own fundamental blueprint, a correction term that has been waiting billions of years to take the cosmic stage. We are not being pushed by an unknown force, but reading the fine print written into the quantum structure of reality itself. The deepest secrets of the cosmos may be written not in forces or particles, but in shape. This is a realm where mathematics transcends calculation and touches on the essence of form itself. Theory 28, the cosmological constant as a topological invariant, ventures into this abstract landscape. It proposes that the value of dark energy is not a dial that could have been set to any number, but is instead locked in by the universe's most fundamental, unchangeable feature, its global topology. Topology is the study of properties that remain unchanged even when you stretch, twist, or deform an object, as long as you do not tear it or glue new parts together. A classic example is a coffee mug and a donut. To a topologist, they are the same object because each has one hole, the mug's handle and the donut's center. You can, in theory, smoothly deform one into the other. That hole is a topological invariant, a piece of data that defines the object's essential shape. Now apply this to the entire cosmos. Our universe, according to general relativity, is a four-dimensional spacetime manifold, a mathematical fabric that can be curved and dynamic. This manifold, like the donut or the mug, could have an overall topological shape. One of the most powerful topological invariants for such a shape is called the Euler characteristic. It is a single number, often denoted by the Greek letter chi, that captures a fundamental aspect of the manifold's architecture, related to the number of holes, handles, or boundaries it possesses in a multidimensional sense. In some of the most advanced attempts to formulate a theory of quantum gravity, particularly those inspired by string theory and holography, the cosmological constant does not appear as a free parameter you plug into the equations. Instead, it emerges as a quantity directly proportional to this Euler characteristic. The lambda in Einstein's equations becomes tied to chi, a number that is fixed once and for all by the topology of the spacetime in which we live. Imagine the universe as a magnificent multidimensional sculpture. The cosmological constant is not a color painted onto it that could have been different. It is more like the number of fundamental loops or tunnels carved into the sculpture's very substance. That number is an intrinsic part of its identity. If the universe's topology were that of a four-dimensional sphere, the Euler characteristic would be one number. If it were more like a four-dimensional torus, a hyperdonut, it would be 0. Each possible shape yields a specific fixed value for chi, and therefore a specific fixed value for the cosmological constant. In this view, the puzzle of fine-tuning dissolves into a question of classification. We do not ask why lambda is so small, we ask, what is the topological shape of our universe that yields this particular small lambda? The value we measure is then a cosmic ID badge, a direct readout of the universe's most basic geometric identity. It transforms dark energy from a mysterious energy into a geometric birthmark. While this idea is profoundly elegant, it resides in a highly speculative mathematical domain. We have no way to directly measure the global topology of the entire universe, as we can only observe a finite part of it. Furthermore, for this to work, the topology must be fixed and non-dynamic, a rigid scaffold upon which the energetic drama of particles and fields plays out. Yet, it offers a breathtaking possibility that the force accelerating the cosmos is not a contingent detail of physics, but a necessary signature of what the universe fundamentally is, a number written in the indelible shape of reality. Two shadows in the cosmos may be whispering to each other. We have treated dark matter and dark energy as independent actors, one clumping silently to build galaxies, the other spreading smoothly to tear them apart. But what if that independence is an illusion? Theory 29 dares to connect them, proposing a cosmic dialogue where these two dominant unknowns exchange energy in a hidden embrace. This is the idea of interacting dark energy. It challenges the foundational assumption of the standard cosmological model, which is that dark matter and dark energy evolve separately, their densities diluting with the expansion of space according to their own fixed rules. In an interacting model, they are coupled. A conduit exists between them, allowing energy to flow from one reservoir to the other. Think of it like two interconnected water tanks on a vast cosmic ship. As the ship sails through expanding space, water can be pumped from one tank to the other, changing how much each one holds over the voyage. This simple coupling has profound power to reshape cosmic history. The most pressing puzzle it addresses is the coincidence problem. Why does the era of dark energy domination begin roughly at the same time that complex life emerges? In the standard model, it is a staggering accident of timing, but with an interaction, the rise of dark energy is no longer an independent event. It becomes choreographed by its link to dark matter. In one compelling scenario, energy flows slowly from dark matter into dark energy. In the early universe, dark matter was overwhelmingly dominant. As it clumped and provided the gravitational seeds for all structure, it was also steadily feeding its energy into the dark energy field. This transfer was initially a tiny trickle, but over billions of years, as the dark matter reservoir slowly depleted, the dark energy reservoir grew. The timing of dark energy's takeover is then a direct result of this long-term transfer. It did not just happen to become dominant now, it was programmed to do so by the rate of energy exchange set in the early universe. The coincidence is engineered by the interaction itself. The models for this coupling are as varied as they are ingenious. The interaction can be phrased mathematically as a source term in the continuity equations, a little plus or minus sign that links their evolution. In some models, the rate of energy transfer is proportional to the density of dark matter. In others, it is tied to the expansion rate of the universe itself or to the density of dark energy. Each model paints a different narrative of the cosmic relationship. Is dark matter decaying into dark energy? Is dark energy imparting a kind of friction that slows dark matter particles? The implications ripple outward, affecting everything we see. This interaction would leave distinct scars on the universe's structure. If dark matter is losing energy, its ability to clump under gravity is altered. The growth of galaxy clusters and the vast cosmic web would proceed at a different pace. Furthermore, the cosmic microwave background, that fossilized snapshot of the infant universe, carries an imprint of how matter was distributed before galaxies formed. An interaction between the two dark components would tweak that imprint in specific ways, changing the precise heights of the acoustic peaks in the CMB power spectrum. Astronomers are already using data from the Planck satellite and large-scale galaxy surveys to hunt for these subtle deviations. So far, the evidence for a strong interaction is weak. The standard non-interacting model still fits the data remarkably well. But the door is not closed. Future observations from the Vera C. Rubin Observatory and the Euclid Space Telescope will measure the growth of structure with unprecedented precision, offering a decisive test. Perhaps the two greatest mysteries of the cosmos are not separate puzzles, but two sides of a single, hidden mechanism, a secret exchange of energy that has quietly orchestrated the fate of everything from the largest void to the possibility of our own existence. Our final theory is the most unsettling of all. It suggests the accelerating universe, the foundational evidence for dark energy, might rest on a colossal mistake. This is not about inventing new physics, but about questioning the very data that convinced us. Theory 30 asks, what if dark energy is an illusion born from a subtle, systematic error in how we read the cosmos? The case for acceleration stands on a precise chain of observation. We see distant supernova appearing fainter than expected in a universe decelerating under gravity. But that entire chain depends on assumptions, and if any link is weaker than we think, the conclusion crumbles. The first potential crack involves the supernova themselves. We use a specific type Ia, as standard candles, assuming they all have nearly the same intrinsic brightness when they explode. This lets us judge distance by how dim they appear. But what if that standard is not so standard? Could supernova from billions of years ago, when the universe was younger and metal content was different, have been intrinsically fainter? If we mistakenly assume they were as bright as modern ones, we would overestimate their distance, creating the illusion they are farther away in an accelerating cosmos. Astronomers have searched tirelessly for this evolutionary effect, comparing supernova properties across cosmic time, and so far, the standard candle assumption holds remarkably well. But absolute certainty is a phantom in science. Another shadow falls across the light itself. Intergalactic space is not perfectly empty. It contains fine dust. This cosmic dust can dim and redden the light from supernova, mimicking the effects of greater distance. We correct for this extinction using models, but what if our models are wrong? What if the dust in the early universe was different, grayer, and less reddening than the dust in our galaxy? If we apply the wrong correction, we could again misinterpret a dimmed supernova as a distant one, fabricating the signal of acceleration. Teams have cross-checked with other distance indicators and studied dust properties in distant galaxies, and the acceleration signal persists, but the nagging possibility of an unknown systematic remains. The deepest assumption, however, is cosmological. Our entire interpretation rests on the cosmological principle, the idea that the universe is homogeneous and isotropic on the largest scales. We assume the laws of physics and the behavior of light are the same everywhere. But what if that is not entirely true? What if, on scales even larger than our surveys, there are gradients in fundamental constants or in the properties of the interstellar medium? Such a large scale in homogeneity could bend light or affect brightness in ways we do not yet comprehend, skewing our cosmic ruler. Finally, there is the cornerstone of expansion itself, redshift. We interpret the stretching of light from distant galaxies as a Doppler shift caused by the expansion of space. But could a small fraction of that redshift be due to something else? Centuries ago, light was thought to simply tire as it traveled, an idea called tired light, though it was discarded because it could not explain other observations like time dilation in supernova light curves. Yet the door is not completely sealed. Could there be another, more subtle interaction between light and the fabric of space over billions of years that contributes a tiny, cumulative redshift? If so, our expansion history is miscalibrated, and with it our need for dark energy. The evidence for acceleration is a tapestry woven from multiple, independent threads, not just supernova. The cosmic microwave background, the large-scale structure of galaxies, and the integrated Sachs-Wolf effect all point to the same conclusion. This convergence makes a single, simple error unlikely. Yet, science progresses by questioning its foundations. The possibility that dark energy is a monumental misinterpretation, while slim, is the most important possibility of all. It forces us to be humble, to check and recheck our instruments and our axioms. For if we are wrong, the universe holds a secret even more profound than the one we think we have uncovered. The journey through these 30 theories is a map of human curiosity itself. We have ventured from the ghostly pressure of Einstein's abandoned constant to the phantom menace of a cosmic rip, from the holographic projection of reality on a distant screen to the chilling possibility that our universe is a rare, habitable bubble in an infinite multiverse. We have watched gravity leak into extra dimensions, seen fields awaken in cosmic voids, and pondered whether the acceleration we measure is even real, or a grand illusion born from our place in a titanic emptiness. Each idea, from the elegant mathematics of unimodular gravity to the thermodynamic push of a cosmic horizon, is a different kind of torch, casting its own unique light into the same profound darkness. None have yet illuminated the full truth, but together they reveal the breathtaking scope of the mystery. Dark energy is not a single puzzle, it is a frontier. It challenges the foundations of physics, the nature of reality, and our place within it. The fact that we can conceive of such a stunning array of explanations, from the granular structure of spacetime to conversations between dark siblings, is a testament to the power of the human mind to reach into the unknown. So, the exploration belongs to you now. Which of these paths feels most compelling? Does the holographic universe resonate, or does the stark logic of the anthropic principle shake your sense of cosmic specialness? Perhaps the terrifying elegance of phantom energy or the quiet engineering of the Fab Four fields captured your imagination. Share your favorite theory in the comments below and tell us why it speaks to you. What questions did this journey spark? The conversation is how we push the light further into the dark. If you want to keep exploring the edges of understanding, to dive into the mysteries of black holes, the multiverse, or the quantum origins of everything, be sure to subscribe. Our universe is stranger than we can suppose, and the next revelation is always waiting just beyond